Hi everybody and welcome back. So it's been a week or two since I've been able to get back down here to the bench. Things have been crazy at work. But where we left off on our last video, we were talking about amp bias, and I kind of left you hanging on a few things. So we're going to spend this video going over a couple more notes about tube bias in guitar amps, and then we're going to kind of finish this amp up and test it however we can. I do have some guitars and things, and I'm not a guitar player. I played bass a little bit in a previous life, and I did vocals and keyboards, but really two of my friends were fantastic guitar players. They were cousins, so they were always kind of pushing each other to the limits, and they were, why should I get involved in that when they were so amazingly good? It was a lot of fun. Anyway, as you can see, we have the amp back together. We have a few things we want to finish on it, and then we can test it out with my really poor, not having touched a guitar in many, many years abilities. But at least hopefully we can get two chords out and hear what it sounds like. I don't know. So let's talk about the biasing questions. We were talking about where and how you measure the bias, and the method that I showed you was kind of complicated, but it's also the most accurate way. I received a lot of really good comments, so I want to kind of mention a few of those and to share them with all of you, and hopefully this will explain some things, and then we can get back to testing our amp. So if you remember, we were talking about checking the bias, and we were measuring the current flowing through the tube, and then we were measuring the voltage applied across the tube between the anode and cathode, and then we used simple Ohm's law to calculate the actual wattage, because we know that the wattage is equal to volts times amps. And in the DC world, which, we're talking at idle, so this is at DC, that's going to tell you what your idling power is going to be. And of course, in these amplifiers here, the Marshall style and so forth, these push-pull amplifiers, we usually bias them somewhere around that 60 to 70% of their maximum rating. Now, with Class A amplifiers, I'm not going to get into amplifier classes and things on this video, but you typically would bias the amplifier at its maximum power, close to 100%. And there's reasons for all of this. But anyway, one of the things we didn't cover, and we're talking about fixed bias right now, not cathode bias, is when we look at the tube characteristics. If you notice, when they talk about the current, the idle current, or the maximum current, I should say, in this instance, they're saying that your anode current should have no more than 100 milliamps. And this is very dependent upon the voltage, because really the main thing we want to make sure is that we do not dissipate more wattage than the tube can handle. So if you look up here, your maximum amps or wattage for your anode is 25 watts. So they don't want more than 25 watts of anode power being dissipated by the anode. But if we look down here, there's another watts rating, and it's WG2. So what is G2? Well, if we come over here, G2 is your screen grid. And if you go back to our video series on the Fisher X101C, we get into some of this with the screen and with pentode versus beam tetrode and all these things. But we talk about what these grids do. And G2 actually has a maximum rating, and it's 8 watts. Now wait a sec.
It is here. This was the old way. This means 6 qadam high.
About 72 inches.
Wait! then take back one kadam.
What does this all have to do with anything? Well, when you apply your screen grid voltage, it's going to dissipate a certain amount of power as well, and it is going to draw current. And that current is going to be referenced to your cathode. So the current being dissipated by the anode and the current being dissipated by the screen grid are actually two separate current loops. And when you measure at the cathode, so like if I lift the cathode, if I lift pin 8 and I put a resistor in there or put an amp meter in there and measure it, I'm actually measuring the sum total of anode current plus my screen grid current. So what I'm reading here is actually not only the anode current. Now, this is so much smaller than this that a lot of people will ignore it because it's close enough. But just be aware that this is going to draw about 5% of the current that the anode is actually going to dissipate. So there will be about 5% of this amount of current flowing here. And down here, it's going to be both of them added together. Let's make it a little simpler. So I redrew this tube. This is not really what a tube is, but we're doing an equivalent circuit right now. So if you notice, I have your G1, which is your control grid. That's where your signal comes in, from your driver stage, or from your preamp stage, whatever you want to call it. And it affects the equivalent resistance of this circuit. Okay, so that's what our bias is doing. But really, when we look at this, we have two current paths. We have your anode, B plus, going into your anode with respect to the cathode. And there's a certain amount of current flowing through there. Then we have our B plus for the screen grid, which is going to be usually this with a dropping resistor attached to it. So you'll have, in this amp here that we're working on, it's a 1K resistor. So they'll take a 1K resistor from here and attach it to here. So you'll have a slight voltage drop. But for the most part, you have B plus going in here. You do have a minimal amount of current flowing through that screen grid with respect to your cathode. So if you really measure right here, if I put an amp meter right here, you're actually looking at this and this together. Whereas if I put my amp meter up here and measure, I'm only reading this node with respect to this point. Does that make sense, or am I confusing everybody? So, again, this is a very small amount of current compared to this. So if we have, let's say we were looking at 30 milliamps, remember 32, 33, that's where we set this for up here, doing our little calculation with that method I showed you in the last video. There's probably going to be another 5 or 6 milliamps flowing through here. So if I measure it down here, if I measure 35 milliamps down here, I'm really only going to have about 30 milliamps up here. Now, this doesn't hurt anything. It just means that you're going to under-bias your tube a little bit. And all that's going to do is make the tubes last a little longer because they're running cooler. However, when you start getting into the more detailed things about how the amp sounds, at what point the tube is going to go into clipping and cause distortion, things like that, how the tube reacts under a signal, it will affect it, and it does make a difference. For non-musicians, it doesn't matter. But for somebody who's a very serious musician, who has a lot of experience in guitar playing and so forth, they actually care a whole lot about those sorts of things because it affects their sound of their guitar. I said in the last video before this one that a guitar amplifier is every bit as much of an instrument as the guitar that's plugging into it. And this is why. Every little change that you make to this amplifier affects its characteristic and how it reacts to the guitar that's plugging into it. What gives a guitar player their characteristic sound that they have is not only their technique and their professionalism and experience, but also the instrument that they're playing and the amplifier and so forth that they're plugging that instrument into. It all comes together to make a characteristic sound. And that's why a lot of times you can turn on, even non-musicians, just from you listening to music, you can turn on a song and play a song, just a couple of chords, and you immediately know the artist by the way it sounds. Anybody that's listened to AC/DC, when you hear that sound, you know it's Angus Young or Malcolm. They have their own sound. And even though it's a very simple rig that they use, it's very characteristic. You can't miss it. And I can go on and on and on and name almost every musician that's well known. They all have their characteristic sound. You can tell them differently from everyone else. So anyway, I just wanted to share that with you. If you measure the current down here, understand that you have to subtract about a good rule of thumb on a 6L6GC or an EL34. You want to subtract maybe about 5 milliamps or so from your reading here to get a rough estimate of what's up here. You'll be pretty close if you do that. But just remember, if you use one of these, like this, one of these little breakout sockets, you're actually measuring down here, not up here. Now, another thing I want to talk about is that tubes aren't necessarily, when we measure this method using the anode to the cathode, and we measure across the winding resistance, and we calculate our current, remember that? We can compare this side to this side, and we did that, if you recall, and they were very closely matched. So, no problem, right? But what we didn't know was if these tubes here are matched to one another. We know that this pair was pretty closely matched to this pair. If you remember, we were within 1 milliamp or so of one another between these two sides, right? But that being said, we don't know by measuring this method, because for all intents and purposes, these two tubes are just completely wired together in parallel. You can see the anodes are tied together, the cathodes are tied together. The screen grids are mostly tied together through these two resistors. The control grids are tied together through these two resistors. So these are running in parallel. So although we know that this pair has the same dissipation as this pair, they're very well matched, we don't know if these are matched to one another and these are matched to one another. In other words, if you remember, we have two completely different tubes in there. We have a JJ and we have a Ruby tubes, which is, rebranded Marshall. But they're different tubes. Even though they're both EL34s, they may have some different characteristics. In other words, they may have slightly different bias characteristics in that the bias voltage, the negative bias voltage you apply, may need to be slightly different to get the same amount of dissipation at the output. And we don't know that unless we can measure each tube individually. That's where those silly little sockets come in that allow you to break that cathode circuit and measure it down there. So that's what we're going to do. Remember, these seemed to be matched, but let's look at it now. What I'm going to do is I'm going to put this tube and this tube each on one of those breakout sockets. And we're going to measure, even though we're going to measure cathode current right here, we know that it's going to be a little bit lower at the anode because we're looking at the sum total of cathode plus screen grid. But we don't care. We just want to see if this tube and this tube are both conducting the same amount. I'm going to guess they're not, right? And so we're going to do that. But what I do think is that this tube and this tube are matched, and this tube and this tube are matched, and the total of these is matched to the total of these, but this one and this one may not be matched, and this one and this one may not be matched. So again, let's check and see. If you notice, they did one JJ on each side and one ruby tube on, so they had one of each on each side to split it up. So I'm going to connect that up, and I'm going to go up and show you. So I have two individual meters. Each meter, let me fix the lighting a little bit. Each meter is measuring one tube on one side. So in other words, this meter here would represent this tube, and this meter here would represent this tube. And if we look, we have our little breakout sockets connected, and we have one JJ tube and one ruby tube. And I have the amp in standby right now, so I don't have the high voltage on. I'm going to fix the camera right now so it's stable. And I'm going to move this light a little more. And now let's come out of standby, and let's see. 1 millivolt will represent 1 milliamp of dissipation current, okay? So let's flip it. And if we look as we apply the voltage, they're going to kind of settle in. And look at that. We have 32 milliamps total. Remember, you have to subtract about 5 milliamps or so for the screen grid. And on this one, we have 42. So there is a 10 milliamp difference between those two tubes. So even though this side is matched to the other side, this individual tube is not matched to this individual tube. And I would say that if we move these to the other side, we're going to see similar results. They're going to be out the same amount. So let's do that. We now have the tubes moved over to the other side. I'm going to turn the amplifier on to get it to heat up. And while it's warming up, I want to talk to you about another thing with vacuum tube amplifiers. Whenever you turn on an amp, especially a guitar amp like this, it is highly recommended that you do not run the amp without a load connected to the output. In other words, either have a speaker connected or a dummy load, as I have, but make sure you have a proper impedance load put onto the output transformer. A long time ago, I did a video on output transformer impedance, and I showed you a little spreadsheet I made of how the impedance changes with the load that you apply to it. What that does is, by changing that, it will change the actual impedance and the load and the current that's being put on the tubes. Not so much at idle, but absolutely when the amp is operating, when AC power is going through those tubes, it will majorly affect the load on the tube. So make sure you always have a load connected to your amplifier whenever you're powering it on. Okay, so let's tighten the lock down here on the stand, and let's take a look at what happens. How about that? So what we're seeing is the ruby tube is always, the ruby tubes are perfectly matched because this was actually over here, the socket. So 42 milliamps again, and this one's 35. So the JJs were not as matched, if you remember. The JJ had about 32 milliamps. So, but they're close. They're very close. But what this is telling me is that the Marshall branded tubes are actually biased a little hotter than the JJs, so they're not balanced. Now, what does that mean for everything? Well, if this amp is biased pretty cool, so all it means is that those Marshall tubes will be handling a little heavier load than the JJs. The amp will work, but the tubes are not matched. And if you decide to run the amp hot, which some people do because it affects that sound that we talked about, you could very well exceed the ratings of those Marshall tubes, but still be within the rating of the JJ tubes. Now, this is not an extreme case, but it is significant enough that you can see the difference if my meter would stay on. So there's a good example of not having matched tubes. Now, riddle me this one. What happens if we would take the Marshall tubes and put them both on one side and the JJs and put them on the other side? You would really have an imbalance between the two sides. So this is why we all talked about matched tubes or matched quads, matched pairs. It's very important to use matched tubes so that the amplifier works in a predictable manner. You can just slap any tubes you want in there, but you'll do it at your own peril. Again, some people purposely put mismatched tubes in because they want to get asymmetrical clipping, which is a sound. It affects the sound. If you know what you're doing and you understand it, go for it. You know, guitar amplifiers have different rules than audio amplifiers, you know, for listening to music. So this is something you would never ever do, for instance, on that Fisher amp that we rebuilt, because it would adversely affect the performance of the amplifier for what you're trying to make it do. Again, guitar amplifiers are a different animal. So I spoke to the owner, long story short, and he wants to put a set of matched tubes in. So that's what we're going to do. We're going to replace these tubes with some matched ones. And then we're going to run this test again just to see what the heck it does. So we have a brand new set of matched tubes. And they all have their little matching marks on them from the place that they were purchased. And they're brand new Electro-Harmonics, made in Russia. And actually, these are pretty good tubes. I like the sound of them. I like the way they perform, and you can't beat the price on them. You can get some pretty good deals on them if you shop around. But we're going to put these in. I'm not going to touch anything. I'm not going to adjust the bias. I'm just going to plug them in place of the other four, and we're going to use our sockets. We're going to test the right side first, and then we'll check the left side, and we're going to compare everything. And then we'll go through and we'll do our calculations again. So we have our Electro-Harmonics tubes fitted into the amp, and they're turned on, and I love the glow of these tubes. They're really cool. And these are the slim ones. If you notice, the Ruby tubes come in the fatter bottle, they call them. And these are the narrow ones, similar to the JJs. None of that really matters. I mean, it's just the design. So let's get down here. Hopefully my meter won't time out and shut off on me. And let's just see where this side is first, and then we'll move over to the other side next. So here we go. And you can see these tubes are really hot. And they're not perfectly matched, but they're within 5 milliamps of one another. So they're matched, but they're also extremely hot compared to the other tubes. These are nice fresh tubes, and I think after they settle for a while, you have to kind of burn a tube in for a while. You have to use them for a while, and then their characteristics will kind of settle for a while. Tube burn-in is really a thing. Kind of getting off subject, but on the same idea, X-ray tubes are like that. When we replace an X-ray tube in an X-ray machine, if it's a brand new tube, just manufactured, it's not uncommon that when we set it, it'll be perfectly within spec and within calibration for radiation output and so forth. And to come back several months later after they've been using it a while and find that the tube has drifted in calibration and you have to touch it up. You have to recalibrate it. So knowing that whenever we install a new tube, we will usually come back in a little bit and we will retest the tube and recalibrate it. And then usually after doing that, it'll settle in and it'll hold those values for a very long time. It'll drift very slowly over time after that. And these tubes are very similar to that. You know, they're vacuum tubes the same as an X-ray tube. And they have a similar characteristic to them where you'll see they'll go through a little burn-in period, then they'll settle down, and then they'll do a gradual change over time after that. So if you notice, the bias was much, much higher. We're going to move over to the other side, and they should be, I would guess they'll each be in that 50 to 55 milliamp range as well. So let's move the sockets over and test the other side. As you can see, our breakout sockets are moved to the other side over here. We have our meters connected once again, and we've let them warm up a little bit, and let's see what happens. Let them settle a little bit. And you can see this pair is a little closer matched than the other side. So the first thing I will do is I will rebias the amplifier, and we'll set it to a reasonable value back where we were using the method that we did in the last video. Then we'll let the amp sit idle for a while and then retake our measurements and then come back and touch the bias up again. And then the amp it'll be what it is for a while. And after the owner plays it for a while, that value will drift a little bit. You'll touch it up and it's good to go. So that's what we're going to do next. Here's the setup. We're back to our original measurement. I kind of want to show you how this all works and why we measure things this way. So if you look right now, we're measuring across the primary of the output transformer. So we're measuring from the blue wire to the center tap and from the red wire to the center tap. And we're going to measure that voltage drop. Now we remember from our previous video that the winding resistance is a little different between the two. One side, the blue side, was 16.95 ohms, which is about 17 ohms. And the red side was 15.74 ohms. So they're about 1 ohm difference, roughly, little over an ohm difference. And that's normal, as we said before. Most transformers are wound that way. That's the way they are. So we're going to measure those two voltage drops. So just remember, that's how it's hooked up right now. I'm going to move the camera up and set it up on the meters, and we'll take our measurements. So our top meter represents the blue side, or the side of the transformer with the blue wire. The bottom meter is the red wire. And when I apply power to the amp, we have very similar voltages. So if you look at this top one, this would be, once again, the blue wire. So we're going to write that down, 1.1, let's say 1.15 volts. And if we look at the red side, it's also about 1.15 volts. All right. Let's go down and do our math. So looking at this, you can see that they're not matched, right? And I would say this is not a very matched pair. But we really have to finish doing our test. So we know we have 67.8 milliamps on the blue side and 73 milliamps on the red side. Now let's measure our voltages from anode to cathode. We now have our meters connected between the anode and the cathode, across the anode and cathode of each side. So you can see the blue side and the red side. And we're going to go up to our meters now. We're going to turn it on. And remember, the top is the blue side and the bottom is the red side. And we have about 466 volts on each side. So 466, 466. And it floats around again. So maybe we'll call it 465, let's say, because now it's settling. And if we look, here's our results. The blue side is about 31.5 watts, and the red side is about 33.9 watts. So they're about 2.5 watts difference between the two sides, which is not huge. That's not really bad, especially when you're using ganged tubes like that. So now if you wanted to get closer, you could actually juggle the tubes around a little bit and move the tubes from side to side until you get the match that gets the closest. Or you could just leave it alone. But that's essentially it. And these are not the world's most matched tubes from what I'm seeing here. They were sold as a matched set, and you notice the little sticker on them all said they were perfectly exactly the same. They aren't. So if you recall, these were all boxed together and they had this rubber band holding them together. And they all had these little red stickers with the number 40, right? Well, I don't know what 40 is, do we? We just know that if they're all 40, they must be matched, right? Well, you need a little more information than that. If I open this up, that 40 that you were reading was the milliamp rating of the anode current. But that test was done at 400 volts with negative 36 volts applied to the control grid. And if you recall from our earlier tests, this amplifier applies about 465 volts onto the anode of the tube. And we're biasing the tube at about negative 43.8 volts. So why should that matter? Well, there's a reason. When you statically test a tube, that's actually the preferred way that a lot of people will match tubes. A lot of times when you hear using a tube tester, so we have a tube tester, and the tube tester can check a couple different things. The simplest vacuum tube tester is called an emissions tester, and we've seen those on this channel before. And all they check is to make sure the tube is conducting something, but there's really no load on it. So what people will do is they will build these test jigs where you will apply a set voltage and a set bias voltage to the grid, and then you'll measure the associated current with that at that static voltage and that static grid voltage. And you'll pick 4 tubes that all perform the same at that particular spot. The problem is that a vacuum tube is not totally linear. In other words, you need to check another factor that we call transconductance. And transconductance is a measurement of how well a tube will conduct with a given signal applied to it. And the problem is, as you change that grid voltage, that, for instance, the bias voltage, the negative voltage, the amount of conductance of that tube will not change linearly. So it is possible for a set of tubes to match perfectly at one point, one amount of plate voltage and grid voltage, control grid voltage, bias voltage, but not be the same at a different plate voltage and a different bias voltage. And what you just saw was an example of that. So the person who matched these tubes was not being dishonest. As a matter of fact, they shared the point at which the tube was matched. It was matched at 400 volts with negative 36 volts bias. And if we were to set up a test jig and apply those exact amounts, I would venture to guess that all 4 of those tubes would fall right into line. The problem is we did not test the transconductance of the tube. And by not knowing what the transconductance of the tube is, or plotting the curve, like on a tube curve tracer, which none of us have, they're very expensive, very rare. It is possible for things like that to happen. So just understand, when you get a set of matched tubes, it depends on how those tubes were matched as to whether they truly will be matched in your amplifier or not. Pretty crazy, isn't it? But that's how it works. Now, if you had an amplifier that had a 400 volt plate voltage and you were running about that type of bias voltage on there, these tubes probably would fall into line and they would match up pretty well. But there's the factors of the amplifier will affect that. Or if you matched the tubes perfectly for transconductance, in addition to doing that test, chances are they would match. And the thing is, when tubes are matched on a curve tracer or with transconductance the proper way, no matter what bias you set them on, they'll track to one another very closely. So there are different types of tube matching, and I think that's what I'm trying for all of you to take away from this. So yes, these are matched tubes, but they weren't necessarily transconductance matched, and therefore in this particular amplifier, because the matching characteristics that they used were different than the characteristics that the amp actually puts on these tubes. So as a result, these tubes look to be somewhat mismatched. Now, how far they're off, that's really the big question. If they're close and you're within a couple of watts from one channel to the other on a 100 watt amplifier, it's not really a big deal and I wouldn't worry about it. But understand that there is a difference. And that's why these 4 different brands, you have 2 different brands of tubes here. But yet, when you kind of split them up like this, they worked. And they worked about the same as our quote-unquote matched tubes. So, just gives you a little bit of an idea of all that. And again, I don't have a vacuum tube curve tracer. And my transconductance tester, which is my Heathkit TT1, is on the fritz, so we can't really do that. And even that Heathkit one does not do a perfect job of matching the tubes. There are some models out there that do a really good job, but unfortunately they're very expensive and I don't have one. I may get one day. As I get closer to retiring or whatever, I'm going to do more of this hobby, and it may justify me getting one of those at that point in time. But for right now, I don't have one. So there you go. And the best tube matching device you have is your amplifier. Put the tubes in the amp, do the measurements I just showed you, and you're going to know how they work in that particular amplifier. So you really don't need expensive matching equipment unless you're going to buy bunches and bunches of tubes and match them to resell them. So I hope that was a little bit interesting to all of you, and hope that gives you a little more insight on tube biasing. So we have our amplifier connected. I have a signal being fed into it, and I'm feeding 440 hertz. So we got A440 going in there for you guitar players. And I'm going into the low sensitivity input because the high impedance on the high input would not be very good with this signal generator without some extra coupling resistors and things. But we're going to go into the low input and with 150 millivolts signal level. And I'm going to focus you in on here. And we have our unmatched matched quad of tubes, and we biased them correctly, and we swapped them around to get them as close to one another as possible. And let's just see how well this thing performs. What we want to find is if we have even clipping or asymmetrical clipping. In other words, if the top and the bottom start to clip at the same time. So let's check it out. All right. And you can see right about there it's starting to clip. And it is clipping almost equal on both sides if you look. If I go down to about there, we have about 20, let's call it 26 volts. That pot's noisy. 26 volts RMS, right? So if we go, let's come down here and do the math, right? Yeah, I have my cool calculator today. So if we go 26 times 26 equals, and then we take divided by 8 ohms, you have about 84.5 watts. And remember they were calling this a 100-watt amplifier? Well, remember we biased this amp cool. We biased it only at about 62% or so. So, you know, of maximum power. This is not 62% of your of 100 watts, obviously, but it is not quite 100 watts. And if you biased this amp to put out a full 100 watts, you would be running those tubes really, really hot. So, number one, we know that the amplifier is clipping correctly, that the tubes are working pretty well, and we know that the amp is putting out a clean 84.5 watts before it starts to break up and clip. And this is without having, I'm not overdriving the input, I don't have the distortion on or anything like that. So there you go. We're now looking at a very small signal. We're at 200 millivolts per division, and we're looking at peak to peak. So really we only have about 236 millivolts RMS, which is very low power. And the volume pot on this thing really could use replacing because it is noisy, and if the pot's all the way down as far as it'll go, and you're still getting that much volume leaking through, which again, this pot is old, and that's probably why it's doing that. But you can see there is no crossover distortion whatsoever. And so the amp is working perfectly there. So again, this amp is good. It's working very well, and it's ready to try out on a speaker in the real world. So a couple things before we test this amp out. First of all, my guitar speaker that I have a 410 cabinet that I built a long time ago. It's in one of my storage units at work, staying out of the way because it's kind of big. And I have to go and dig it out and bring it over here before I can plug that amp in. Second of all, I just thought I'd give you the nickel tour of my guitar. I had a few people ask about it. So it needed restrung. The strings that were on there were getting rusty, and they were probably 13 years old or so. This is a guitar I built. It was an experiment. It was something when I was getting into guitar building a little bit, and I did a lot of different things that I wanted to try. I did all on this guitar, so it doesn't all make sense as far as how you would build a guitar, because I used some elements that it's one of those things where you would have either or. I did both, but there's a reason for that. Again, this guitar was an experiment. As it turned out, I liked it. I liked the way it played and felt, so I just kind of kept it all these years, and I actually, you know, played with it a little bit. Again, I am not a guitar player. I haven't touched a guitar other than to play a power chord to test an amp, make sure it works, in years. So don't expect me to be much of a guitar player at all. But I did build this. As you can see, it's your basic Stratocaster body. I modified it for me a little bit. I made the width a little bit narrower than a regular Strat. I did the cut in, the comfort cut in there. I did it a little bit deeper. And I think that's something that some companies like Ibanez and so forth did in the past. So hand cut, this is a piece of ash. It's a single piece. We have a lot of Amish or Pennsylvania Dutch population living in our area, and I had access to some pretty good wood shops that, you know, lumber yards where they actually cut and air dry lumber, and that's where this came from. The hardware is just generic Chinese hardware. These pickups are EMG made, although it's their low-end brand. Everything was cheap on this. I didn't go real high-end because this guitar was an experiment. And believe it or not, these are both double coil pickups. The front one is a stacked double, and believe it or not, it's a little bit hotter than this rear pickup. So the other thing is I went with the extra frets on this. I believe you can kind of see the fretboard overhanging. We'll talk a little bit about the neck. I used the Tune-O-Matic bridge. Like I said, it's an amalgamation of different guitar designs that I tried. The most interesting thing was when I made this neck. This is all handmade. It does have somewhat of a compound radius on it. I did my own frets and everything. The fretboard is actually made of Purple Heart. Why Purple Heart? Well, it's a good hardwood, and I had some of it in my wood shop left over from another project. It's a laminated neck with a fretboard, and then the neck is hard maple. And even though it's a laminated, it has a skunk stripe on the back, and it has a double action truss rod that I did. And I was trying this just to see what it would be like. Kind of wanted to work with both techniques, so I did both of them on this same neck. Normally, you would either have the skunk stripe with the one-piece neck, or you would put your truss rod on the slot on the front under your fretboard. But again, it was all an experiment. It worked out really well. As far as the neck design, it's all hand carved. I made this all with some handmade carving tools that my uncle, who's now no longer with us, designed and made many years ago and gave to me. The radius of the neck and everything is similar to the really old Fender C necks. However, the center of where it curves is actually lower. So in other words, it's a little bit wider in the bottom and a little bit thinner on the top. I made it to fit my particular hand. I don't have really super large hands, but it fits the way my hand is shaped. It fits very well into that. That's why I carved it that way. Believe it or not, when I plugged it in and played it, it set up really nice. The intonation came in perfectly, and it really actually sounds pretty good for a kind of a hacked together homemade guitar. Let me go to the headstock here. And you can see on the headstock, I hand cut the nut from bone, and just cheap tuners. So bolt-on neck. Truss rod is adjustable from underneath, so you kind of have to either pull the neck out or remove the pickup. It's not an easy thing. The thing is, though, this neck, the way it's designed, is so stiff, it hardly has any flex whatsoever. So once you get it set straight, it holds very well. These are gauge 10 strings instead of gauge 9. I feel, I'm a fumbly player. I'm not very good. I don't solo or anything like that, mostly rhythm things. So I tend to use a little bit heavier string, a 10 gauge instead of the 9s. So I made the neck to accommodate that. The controls. Kind of a Gibson type switch here for, front both and rear. 3-position, and the knobs, volume, bass, and treble, instead of volume, tone, tone. So another thing, you know, I've done a lot of different wiring configurations. The one guitar that I built and gave to my friend who's a guitar player, it actually has a really nice spalted cherry laminated top on the front that looks really nice. And I did some things with the electronics in that it would adjust the phasing of the coils and so forth as you rotated the pot. It is a really cool sounding guitar. He lives in Texas now. But this was a very early build, probably only my second guitar I ever built. The first one I built worked, wasn't as good as this. I ended up disassembling it for parts and so forth. And then I made maybe I've made maybe 4 or 5 guitars altogether. So I am not a luthier. Don't even try to think that I am. This was just somebody who was puttering around in the wood shop. The frets, I actually had fret wire. I have a fret bender and all those sorts of things to radius them. So they're hand cut. And I actually have a little jig that I use, and I hand cut the slots, you know, with a back saw. That was tedious, but it all turned out and it worked. I didn't even put the fret markers on the side of the fretboard, if you notice, so you can see there where you'd normally have your little dots here, you know, and I didn't even do that. Again, this was really an experiment and I liked it, so I kept it. So there it is. There's the guitar. Nothing special, just a kind of an abomination that I did in my wood shop for entertainment purposes, I guess. So let me, I guess we're kind of on hold until I get that speaker. Once I get it, I will come back and we'll hook it up and I'll play my 2 chords and you can at least hear what the amp sounds like. Very cool. Thank you, Chris. At least we gave everybody a taste of what this thing sounds like. What did you think of it?
It sounds like the old amps. Like, it sounds like the old records, like, instantly.
Cool.
Like, you want to just, like, ring out the chords.
Yeah. Yep. I agree.
Sort of AC/DC style.
Yep. Tell us a little bit about your guitar you just got for Christmas.
This is it's a Schecter Sinister Gates Custom S.
Okay.
It's sort of claim to fame, sort of, almost. Aside from the looks, you know, it's got the Floyd Rose sort of double locking tremolo. Okay. But the big thing is probably the Sustainiac. It's basically just it acts as a pickup when you're in the neck position. Sort of like stratty sort of sound. Cool. Whenever you turn this on, it sort of it'll hold a note forever, you know. Oh wow. And this, it just holds the note. This one, it's sort of a little slower. It might not do it, but then this one, it just goes straight to a harmonic.
Oh, that's nuts.
So you can sort of fake what, you know,
really?
They go up to the amp and sort of make the noises.
But it's actually,
this, you know,
it's the guitar doing it.
You can just have it do it for you. You don't have to sort of find where it, you know, sits, you know. It's controllable.
Ah, the wonders of modern active electronics, huh?
Yeah.
Nice. Very nice. Yeah. Well, thank you again, Chris. I appreciate it, man. I'm sure everybody out there that's watching appreciates it as well. And we're going to wrap this video up, guys. As always, I wish you all peace, joy, happiness, and good health in your lives. Lots of more things coming. Maybe we'll do some more amplifier, guitar amp videos. Let me know in the comments section if you would like me to. And until next time, stay well, everybody, and we'll see you soon. Bye.